So yeah, I also noticed algo exam. Yeah, I know it's that time of the semester. All right, so let's get started. Hopefully, all our panelists for today are in and answering questions. I see some of them are answering. Yeah, there's like a vote for the favorite MIPS register. Okay, let me start sharing something, and then we will get started. Poll number 1 seems important. You notice, huh? Yes. So I heard from several students that they would appreciate an extension on homework because it turned out to be harder. That is than they expected. That is one reason, and the other reason is we actually had a submit issue which didn't affect that many people, but it still affected some students. And so for those students, there might be a delay associated with submitting being not available to grade their homework 3. So that's why I thought an extension might be appropriate, but then I realized that we might have students who, kind of stayed all night trying to finish by yesterday, by the end of the day yesterday. They might be unhappy if we now extend the deadline. So that's why we have the vote. Okay, so I will just go with a majority vote. How you people vote, I will just go with that. Okay, so yes, that's our first poll for today, and yeah, it's open circuits time. Exactly. Have you heard about open circuits before, or are you one of the developers? Yes, if the deadline gets extended, it means that all late day usage will be recomputed by submitting. Okay, yeah, we'll talk about open circuits when we get to gates and actual circuits. All right. So what we need to talk about, let's start. First, half semester mark. I believe it is the last lecture of the first half of the semester. Officially on Tuesday, we will start our second half of the semester. So among other things, that means that people who were helping other students on Submiti Forum, I will gather, so sometime over the weekend or maybe on Monday, I will gather Submiti statistics about the forum usage, and I will look at the people who were most productive, and I will look, of course, into their posts to make sure that it's not just asking questions, it is actually answering, attempting to help other students, whether and whether their answers were exactly correct or half correct is of lesser importance. It is important that people were trying their best to help, and those people will receive extra credit for submitting forum participation as we agreed to do in the beginning of the semester. And then we will do the same kind of stuff at the very end of the semester. So if you haven't been active on the Submiti forum, you can still get some extra credit for that. You still have the semester to go. Okay, so did we get through all chapter 2 slides? Yes. Yes, we did. So we are starting chapter 3A, which is, if you look in your textbook, is not really chapter 3. It is actually appendix B, and we will start with that material today. And homework 3, so we already decided it is going to be due tonight. Well, no, we didn't decide. All right, so there's the vote. Okay, so I will look at the vote outcome after the lecture or during my office hours, which are pretty much after the lecture, starting at 2:30, so that I have enough time to actually get from home to campus, and then I will make the decision. So if you depend on if it's important for you whether we end up moving the deadline or not, please monitor, please check Submiti. When the decision is made, I will just move the deadline on Submiti. That's how you know if the deadline got moved or not. And I will make the outcome of the voting available to you, so you will actually see how many people voted for, how many people voted against, and how many people didn't abstained. Homework 4 will be mostly on the new material, Boolean logic, gates, circuits, and all that kind of stuff. And it will be released over the weekend. I actually have most of it already written. I just need to proofread and double check and solve it myself to make sure that it is solvable. And then I will release it. So hopefully it happens tomorrow. I know some of you asked me to release their homework on Fridays, and I was honestly trying to do that, but I don't think I will be ready to release homework for today. So over the weekend, hopefully on Saturday. Is homework 4 code-based or LaTeX-based? So there will definitely be textbook style problems. They're probably not going to be from their textbook, but they will be, that kind of style where you have to type your answers and put them in the PDF, make them into the PDF. Whether there is a coding part or not, I'm still thinking about it. So I haven't decided. You shall see once their homework is out. You will see. Well, we have to go with some textbook problems as well, right? Because you might not like them, but there are people who hate coding questions, right? So I've heard this before from some students. Oh, just please no MIPS, no more MIPS coding. And then similarly, I've heard from some people, oh please no more C coding, no more malloc and all that kind of stuff. So yeah, sorry, I don't have any good news for those of you who would like, some of the major topics in our course to never appear again. It's very unlikely. Sorry, not much I can do. Yeah, MIPS is not going away. It's going to stay with us until pretty much the last lecture. All right, and then exam 3 grading. We are over 50% done, so our TAs and mentors are working on that. So just bear with us. They are doing everything they can. Their average grade looks pretty decent so far, because as you know, we made problem 6 extra credits, so their whole exam is out of 80 points now, and that of course helped. So the average is actually looking better than on exam 2. Okay, so lab 4 was this week, so hopefully you liked it. But please feel free to share what you think about lab 4. As usual, solutions will be posted on Monday, but you should have by now you should have your own solutions. So the only reason we post solutions is just to give you maybe another way of looking at the problem. So look at our solutions and see maybe maybe your solution was correct, but maybe it was different. So you can get exposure to different ways of solving the same problem. Okay. And yeah, someone says multiplication homework 3 not so much fun. Well, I have maybe bad news for you if you don't like multiplication. So we are going to have more multiplication and division because we will look at computer arithmetic much closer. And this actually starts very slow with primitive gates, but it will get to the actual hardware that performs your addition, subtraction, multiplication, and all that kind of stuff. And it gets pretty complicated. So, just a heads up, we have to look into that. That's really what a computer is, right? You think a computer is something that you can play games with or can play games at, and well, uh, the answer is yes, maybe, but the real thing is, computers do really compute. So if you are a computer scientist, or a computer science major, you need to know how computers actually compute, how they do, those addition, subtraction, multiplication, and that kind of stuff. So that's one of the big things that we need to do in this course, and that's why it is coming. All right. And we have slides for today, a whole bunch of them. And yes, we will be using open circuits, but I will get to that when we get to our first logic gate. All right, so just a bunch of slides for today. Hopefully say yay. And the rest of the month, probably more slides. So coming up, just a lot of material. It's very dense, and we have to go through that fairly quickly to to get back on track. But we are more or less on track. I just checked with the notes from last semester when this course was taught by another instructor, and we are actually just half a lecture behind. Okay, so not by much. So, and if you look at their schedule, you get an impression that we are a lot behind, but they were a lot behind in the last semester. So that, I guess, that's kind of normal. All right. So we are good. Don't worry about that. All right. So without further ado, and yeah, if we have time at the end of the lecture, please remind me. So I got a request, so to speak, from our TAs and mentors, or an observation from them saying that many students are still struggling with RA register and the whole concept of calling the procedure with this storing the return address in RA and then taking this value and using it to return to the caller, and in general with the stack pointer and saving stuff on stack. And of course, this is something that you need for homework 3. So if you're still working on that homework, that might be helpful. So if we have time, I will ask you to ask questions, and I can explain that topic again a little bit more. Okay. So, and like I said, the material that we are starting now is really Appendix B, and then we'll get to Chapter 3. All right, so it's kind of blended together here. All right. And we will be talking about Boolean algebra. So what is Boolean algebra? Well, it's like your regular algebra with letters that stand for variables, and variables are just placeholders for values. So if you think about it, they are like variables in a programming language, those letters, those identifiers. And Boolean algebra is just a set of rules that are based on the theory developed by George Boole in mid 19th century. And because it's the name of the person, Boole, so we spell Boolean algebra with a capital B. Okay, so that's the correct way of doing that, right? Because it's a proper name. All right, so it's basically a mathematical theory of logic, where logic is really simple because it only has two values, true or false. And then there are multiple uses of Boolean algebra, and Claude Shannon, another very notable person in the history of computer science and informatics. So Claude Shannon was responsible for actually defining what information is, and giving the first official definition of information, and building the whole information theory around that. So, and that was already in the 20th century. So Boolean algebra is extremely important. Okay, and the funny thing is, so in the past, I had students who were trying to do Boolean algebra using Minecraft. So that was pretty amazing. That was pretty creative, and they were trying to even. So one of their assignments later will be to actually, for you to build their ALU, arithmetic and logic unit, which can do addition, subtraction, multiplication, that kind of stuff. And some people were trying to do it in Minecraft, and they didn't get too far. So I think they implemented a subset of operations that were required, but that was pretty amazing, right? So if you if you feel like doing something like that, knock yourself out. Okay. So what do we have? Well, we have values that can only hold two things. And it doesn't matter what we call these two things. We can call them true or false, or 1 and 0. And, we can actually map them to other physical quantities like voltages. So we can say 0 is 0 volts, 1 is 5 volts, or true is 5 volts. So that of course make it very convenient to implement all the things that we are going to talk about now in real hardware, right? So it can be directly linked to electrical engineering or digital circuits engineering, and that's why it is very popular. Do not, however, assume that 0 is always 0 volts, right? So this connection can be actually exactly the opposite, right? So it's important to see the distinction between Boolean algebra, which is just a theory, and its actual implementations, let's say in electrical circuits. Okay, so you can totally create an electrical circuit where false or logical 0 would be represented as 5 volts, and false or logical uh, and true or logical 1 would be represented as 0 volts, right? There are actually there are circuits that do exactly that, and there are reasons behind that. We're not going to go explaining that, because it's really more of computer and electrical engineering stuff than computer science. But it's important to see this distinction. So true or false, or 1 and 0, are purely logical values. Okay, and yeah, there's a joke like this logical something is a fairly known is a fairly known joke, because when you say logical 0, it may mean not 0 at all. Like logical 0 in an electrical circuit can correspond to 5 volts. So go figure. And that's why when we have occasionally because of the holidays at RPI, we have Tuesday that follows Monday schedule or something like that. So I would call it like it's Tuesday, but it's a logical Monday, right? Because we can have this distinction, between the physical day, like Tuesday, and the logical day that RPI wants us to treat that day as something else, as Monday. All right, so there are several operations that we can perform on Boolean values, and of course operations have a number of arguments. So the number of arguments can be 1, 2, and more, and we are mostly concerned with operations that either take 1 or 2 arguments. So there's only one operation that takes 1 argument, obviously, and this is a not. So not is negating the value. It is flipping the value. So if the value were true, then not that value would be false. Okay, and this is denoted as an overbar. So it's Boolean algebra, and we deal with letters. Okay, so letters, they are placeholders for values, right? So we have letter A that can be true or false. We can do some transformations just with letters. Okay, same as with your traditional middle school algebra, right? You don't know what A and B are. If you want to perform certain transformations, algebraic transformations, you can do that. Of course, if you want then to evaluate the expression, you need to know the values, but you don't need to know the values to perform transformations. So the same idea carries over to Boolean algebra, right? So this overbar stands for not, and as you could probably guess, it is not very convenient to write if you can only use ASCII. All right, where is my pen? Just bear with me, please. Check what happened to my tablet. So I want a drawer, but it's not. It got unplugged. Okay, I got it back. All right, so you cannot really draw this overbar if you just use an ASCII, like if you're writing in a text file. Of course, in the homework, if you're using LaTeX, this overbar is very easy to do, so please do the overbar. It is the easiest and the most visual way to indicate a negation. But alternatives, if you are only limited to ASCII, would be exclamation and tilde. Right, so those are alternative ways to indicate not. Oops. All right. So, and yeah, you can use this notation in text files. It is fine. Okay, it's really up to you. But if you are typing homework in Word or LaTeX, then please use the overbar. It is easier. And the reason why it is easier, because like if you have an expression, something like this, right? So this notation clearly tells you that, oh, I need to do A or B and then negate the result. If you're using the notation with an exclamation or a tilde, it's harder because here you have to use parentheses, right? Because if you don't use parentheses and you write something like that, okay, so there not is a unary operation, so it binds with the closest letter. So this is really, if we write it using using our overbar notation, this is that, okay, and not what we originally had, not this. So please be careful. Make sure you use parens as in regular algebra, okay, but even more so if you're using exclamation or tilde instead of the overbar. All right, so and then among binary operations, and we discussed before, so there was a poll on the number of binary operations. And by the way, yeah, remind me at the end of the lecture, we can go over recent polls. I think we didn't go over them, so let's go over them and discuss what the correct answers were. And so one of the polls was how many Boolean functions we have. All right, you know, just given n, the number of arguments, how many Boolean functions we can have, and and the answer was 2 to the power of 2 to the power of n. Okay, and when n is 2, so it's 2 to the power of 4, 16. So there are 16 Boolean functions of 2 arguments, and we are, you know, some of them are more interesting than others. As it turns out, there is something that we will call a functionally complete basis. So we are typically interested in a subset of those binary of those Boolean functions, and that's and we start with just 2, or and and. Okay, and for or we use the plus sign. You can also use a vertical bar because this is or in some programming languages, so you can use that as well. And probably the preferred would be 2 vertical bars, because in programming languages there is a difference between the logical operation and the bitwise operation, and therefore, you know, typically their logical would be the double character, like the double vertical bar or the double ampersand. And then, but this is, you know, this is less preferred in our course. We would still understand it. We would not deduct for this, but this is more like a programming language thing, right? So here in the Boolean algebra, we prefer to use the notation either plus, or there is another notation that looks like that. Okay, so this is called disjunction, and it's just a fancy word for or. Okay, so this, it looks like a, you know, a V or a big V, but this is an operation character. So you can use the plus, or you can use this disjunction character. And for and, they're preferred. So plus or disjunction, you can use either. They are both good, right? And like I said, they're 2 vertical bars. It's okay, but you know, definitely not the preferred way when we talk about Boolean algebra. So for and, it is a dot, which looks like a multiplication, right? And or looks like an addition, but we will talk about it why or does not really perform addition, or the addition that we would like to have. Okay, so addition is not as simple as just oring 2 arguments. So back to and. And is the dot, or you can use this V rotated 180 degrees. So this is called conjunction. Okay, so that's again a fancy name for an and. And you can like similarly to the or, you can use double ampersand for and, but like I said, it would not be the preferred way of doing things. All right, so that's the basics. That's the notation. And then let's go over operators. We've talked about them before. So, a couple lectures ago, we looked at the truth tables of or, and, not, and even another operation called exclusive or XOR. So that stuff should be familiar to you already. So the result of or is 1 if any of their two operands is a 1. So or is similar to addition, but operates on binary values. Well, we will see that it's important to say that it is similar, but it is really not the addition. Okay, and we will see an example that shows why. All right, and it was actually in the notes in the lectures a few lectures ago. All right, so and is 1 only when both operands are ones or both operands are true. And it's important to see here that and is a function. Okay, it's a function of two arguments. So we supply two arguments to inputs, and then this function and or whatever computes the result. As any function, and or it's just a mapping, right? So you map inputs into their input values into the output values. You map input values that are drawn from what is called domain into their range. Okay, and for Boolean functions, everything is easy. Their range, the domain is only true and false. We only have two values, and the range is the same, true and false. Okay, so basically we are mapping. So if we represent this, any generic function using a more math-like notation, so we have a set of two values, true and false. Okay, and then we actually have two arguments for and or and other binary Boolean functions. Okay, so this is our domain. And the function maps that domain, and note it maps in there only in one direction. So it is not necessarily reversible into T and F. And this is the range. Okay. So, TF, two sets multiplied, that would give us, the values like TT, TF, F, T, F, F, and on. Too close to the bottom, like that. Okay, so that's just the product of two sets, right? Just all possible combinations. All right. Yeah, they brought back domain and range from 7th grade math. Imagine 7th grade, and that stuff is still useful. That stuff still comes up. All right. So not very easy, just negation, right? We would sometimes say negation because not negates its operand. We would sometimes say invert, right? Because it inverts, right? When we only have two values, when you flip or invert the value, you go back, you go to the other value because there's only two of them. So all of those terms would refer to the not operation. All right. And of course, algebra would be boring if we couldn't do equations and formulas and expressions. So we can combine letters that stand for Boolean values with all the operations that we just talked about. And for now, we will limit our set of operations to and, or, and not, but because they actually, it turns out, and I'm not going to prove it right now, but so please take my word for it. So you can express anything with a set of three, with this set of three operations, and that's why it is called a functionally complete basis. And then we will learn that there are other sets of Boolean operations that also form functionally complete sets or bases. Okay, so That's why we are limiting ourselves to just these three: and, or, and not. All right, so here's an example of an expression, and if we have, two expressions with their equal sign or not equal, that would be an equation, right? Good news is you cannot really, since we only have two values, you cannot do less than, right? So for Boolean algebra, we do not compare the values for less than or greater than. There is no ordering in the set of values for Boolean algebra. Unlike with our number line, right, where we could, our number line, our integers, our real numbers, they are ordered, not like Boolean values. So, something is easier here than with natural numbers or integer numbers or real numbers. All right, so that's that, and here is a bunch of examples, and we can evaluate certain expressions if we know their values for each of the variables, or if their expression contains our constants, our literals. So true and false, so 0 and 1 are our constants in the Boolean algebra. And so we just perform this. This is an OR. So 0 plus 1, 0 or 1 is 1. 1 and 1 is 1. So we can evaluate it to 1. Okay. So, doing things like that, we can you help me with x2? What is x2? Is A, Y, is it A? Because it's law of excluded middle. Okay, yeah, good. So the observation here is, well, there are certain things that we can observe if we try just the substitution. So imagine A is 1, then we have 1 and 0, okay? And so it's a plus, so it's an OR. 1 or 0 is 1, okay? And then what if we say, well, maybe we just got lucky. What if A were 0? We can say, well, if A is 0, then not A is 1, and the result is still 1. So it turns out that no matter how you slice it, the result is 1, all right, irrespective of what A is. And of course, we would be tempted to say, well, such things, such observations, we want to make into laws so that we can actually use them, okay? And x3, we can do the same thing. So if A is 0, well, we don't even have to compute not A because we know it's going to be 0. If A is 1, well, we are not sure, right? Because we have to check the other argument. Not A is 0, and we know that it is 0. Okay, so we conclude that this is always 0. All right, what about x4 plus 1? And plus, remember, stands for OR. It is 1, okay? Because with an OR, if one operand is 1, OR yields 1, regardless of what the other argument is, okay? Here it's funny, right? We just computed the right-hand side, and with now we have to look at, oh wait, but there are equal signs. So for the first three, it's pretty straightforward. We say x1 is going to be 1, x2 is going to be 1, x3 is going to be 0. We computed them, but x4 is 1, turns out. Okay. So that's kind of mind boggling, because like, oh, but what if x4 had 0 initially? 0 or 1 would still be 1, and then we kind of assign 1 to x4. Okay, so be careful with formulas that have their the same value on the right hand side and on the left hand side. Okay. All right, so now let's talk about laws of Boolean algebra. For the most part, we're not going to we're not going to care with proofs. So as someone mentioned, you have forks for that purpose. Okay, where you do tons of proofs. Hopefully you love it, but we're just going to use the results of those proofs. So let's go over Boolean algebra laws. So like with any other algebra, just a set of postulates and identities. So basically like rules that someone either say they're true, because not everything can be actually proven, or it's a theorem that has been proved and you just need to know the result. You don't have to prove it all the time over and over again. All right, so we want to use those laws to help us come up with simpler expressions that have fewer operations or fewer variables involved. Okay, so because they would be easier, faster for us to evaluate. So they will have a shorter form, which is of course more desirable. And so basic postulates of Boolean algebra, right? And a postulate is something that you basically have to trust. Okay, everything else can be derived, but basic postulates you just have to take as is. Okay, and some of the postulates you can try to prove, but then you would just get to another postulate that it would just be kind of recursive, so you cannot really prove it. Okay, so we have the following laws: commutative, distributive, identity, and inverse, and we are going to go over them in the next few slides. So this is identity laws, and if you look at them, they're kind of similar to our traditional algebra with numbers, right? So if I have 5 plus 0, it is 5, right? So we kind of understand what it is. So why is it called an identity? An identity is it is called because change the value. So this 0 is identity with respect of the OR operation, right? Because a plus 0 is a in Boolean algebra, as it is in where plus is an OR, as it is in math, in arithmetic, where plus is addition. Okay, it is important to remember that identity is always with respect to certain operations. So 0 is an identity for addition, and you would definitely agree that 0 is not an identity for the multiplication. Okay, so this is definitely not so. And it's the same in Boolean algebra, right? So the identity for AND is different from the identity for OR, so and it is 1. And obviously, we discussed before the truth table of AND. So if A is 0, then the result is 0. That is the same as A. And if A is 1, then 1 and 1 is 1. So it turns out no matter how you slice it, the result is exactly the same as A, as the operand that is unknown, right? The operand that is not a constant, the operand that is a variable, right? So that allows us to kind of basically prove very easily, but just enumerating all possibilities that yes, this identity holds. All right, inverse laws. Again, there is a direct analogy with our arithmetic, right? So it is the value that yields a 1, okay? And a 1 can be defined differently. So for an arithmetic, that would be actually 0. And if we want multiplicative inverse, right, then it is defined like that. So 5 and 1/5 are multiplicative inverses of each other. 5 and -5 are additive inverses of each other. Okay, so it's the same here. So A or not A is always 1, and A and not A is always 0. So again, we proved those inverse laws here, right? But just enumerating values. X2 and X3 were our examples of that. All right. So commutative laws, and we're not going to prove it here. Again, you can easily prove it by just enumerating all possibilities for A and B, by just essentially building the truth table of the left-hand side and the right-hand side. And when you build the truth tables and compare, so how do you build a truth table? You just say A, B, and F1, where F1 is, let's say this is F1. Okay, and then do your 0, 0, 0, 1, 1, 0, 1, 1, compute F in each of the cases, and then do the same for F2, B, A, F2, do the exact same thing here, compute F2, and then compare these two truth tables. And if the two truth tables are exactly the same, so every line matches, between these two truth tables, it means they implement the same function. It means that F1 is actually the same function as F2. So the important thing here is to see that, well, it is the same function, but they are different formulas. So this, the left-hand side and the right-hand side are not the same formula. The formula is different, right? A plus B is not the same formula as B plus A, right? Because we swapped the operands, but it turns out that our function doesn't change if we swap the operands of an OR, and that means it's the same function, and that's how we can demonstrate that commutative law with respect to OR holds. Right. So later on homework assignments, on tests, you might be asked, how many formulas can we have for the same Boolean function? And the answer in general is many. Right. We can have multiple ways of writing their formula for the same Boolean function. So their functions are the same if you build the truth tables and the truth tables agree in absolutely every row. That's what defines the function, right? And if truth tables are the same, the functions are the same. Okay? And then we can do the same kind of thing for and commutative law also holds for and. You can swap the operands of and it's not going to change. The function is going to be the same function. All right, so distributive laws. So they are on one hand kind of similar to our traditional algebra, but please be very careful, because not all analogies can be carried over from your traditional middle school algebra into Boolean laws. So do not assume that if a certain formula, if a certain law exists in our traditional middle school algebra, it will be true for the Boolean algebra. Okay, so please refer to these slides as a set of laws that we can just take as granted, right? In any of their assignments or on the exam, you can just use those laws, right? We might ask you to actually tell us which law you use, right? But unless we specifically ask you to prove something, you don't have to prove the laws that appear on those slides. You can just take them for granted, right? So you can just say, oh, I'm making this step in my transformation by applying the distributive law, and that would be sufficient, right? You don't have to prove that the distributive law holds. Do you have to remember the name of the law? Yes, we, at least on the homework, we will ask you to, prove, to tell us as a proof that your transformation is correct, which law you are applying. Okay, because then it makes it very easy for us to check, oh, you applied the law that actually does not exist in Boolean algebra. Okay. All right, so those are distributive laws with for or with respect to and vice versa with for and with respect to or. There are other identities that can be derived from these basic postulates. So laws of ones and zeros, associative laws, and De Morgan's law or De Morgan's theorem. So this one is a very common. This one is widely used. It's very very common. So definitely, well, others are useful as well, but like the laws of ones and zeros are pretty much straightforward. But De Morgan's theorem, as an exercise, try to prove it. Okay, I'm sure you can do that. We're not going to ask you to do this on in this class. All right. So I don't know if you do this in Fox or not, but just for fun and just to test your abilities, you can try proving the De Morgan's theorem yourself. But okay, so let's go over those things. All right. So those are derived. So unlike postulates, you can actually easily prove those. Okay. You don't have to, just to trust. You can actually, prove it based on the postulates. So a or 1 is 1, law of ones. A and 0 is 0, law of zeros, pretty straightforward. And associative laws. Okay, so note that distributive laws are up there with the postulates, but associativity laws or associative laws are here that are like derived laws. And so basically it means that you can change the order in which you perform the same operation easily. So instead of first doing B or C and then doing A or the result, you can first do A or B and then take this result and OR it with C. And similarly and for conjunction. Okay. Note that associative laws, you have the same operation here and here. You have the same operation, right? If it's not the same operation, then you cannot apply associative laws. So then you have to check if it falls under distributive laws, and if it does not, then you either have to prove a new law or you just have to do something else. All right, and De Morgan's theorems or De Morgan's laws. So they help us deal with negation, and basically it means that if we have an expression that is an or, and the result of the or is negated, we can replace or with an and, but we have to negate each of the arguments. Okay, so instead of doing A or B and then negating the result, we can compute the same function if we negate each of the operands A and B separately and then and the result. And then the second De Morgan's rule is see how beautiful it is. See how it kind of almost a reflection of the De Morgan's theorem 1 for on or, and the second one for and is very similar. It just if we have A and B negated, we can just negate A, negate B, and take the or. So they are beautiful. Okay. All right. Oh, and we have another pop quiz. So let me turn it on. And yeah, the notation that I used on submitting, so was I think I used the tilde. So this is something we discussed, right? A tilde is negation, so it's similar to this over bar. All right, and where do I have my poll number 2? Hopefully that's the right poll, but please check. Should be open now. All right, so there are other operators. So Boolean algebra is defined over this 3, basic operators, which we call a functionally complete set or basis. So and or and not, it's not the only basis. We can later on. Oh, it's actually here on. No, it's not on this slide, but we will talk about it briefly. So it's not the only functionally complete set. There are others, but this is one of the most common, and or and not. And that means that you can define any Boolean function using just these 3 operations. So you don't really need all 16 that exist out there for two operands. You can just use these 3. And there are other useful operators which are combinations of the three that we discussed. Some of them are not combinations. So if we look at them, nor is not or, okay, and that's why it's called nor. And basically that means that you or and then you negate. So this is nor. Okay, so you can say A nor B, and it would be the same thing as this. Okay, so nor basically means take an or and then negate the result. Okay, and so obviously their effect would be nor returns a 0 if either operand is a 1, right? Because or would return 1 if either operand is a 1, and when we negate 1, we get exactly this 0. And NAND is also a very common operation, so this is NAND, A, NAND, B. Okay, so they are the same. And yeah, as far as I know, there are no standard symbols for NAND and OR, so you can just write them like that if you want. Okay, so obviously NAND is 0 only if both operands are 1, because that's when AND returns 1, and if you negate that 1, you get a 0, which is exactly NAND. And XOR is 1 if the operands are different, so it's exclusive OR that we already discussed. And yeah, so nor or NAND. So each of them by itself is a functionally complete set. So, try to think about why. So basically, what this statement says is nor is sufficient to represent any Boolean function. Okay, it's a pretty strong statement, right? So we're saying, well, we might need to have and, or, and not. So these three have to go together to be a functionally complete set, right? And by itself cannot be used to express any Boolean function. We need to have all three. But then we say nor by itself or NAND by itself can be used to express any Boolean function. So we only need this one operation, which each of them would be a functionally complete set. Okay, so think about why is that. Okay, and think, I can give you a hint. You might find De Morgan's theorem useful and see how you can maybe use just this one operation to actually perform and, or, and not. So you can kind of show that these two sets, this one, and nor, are actually kind of equivalent in their expressive power, in their number of in the fact that you can implement any function using them. All right, so they are both functionally complete sets. Can you represent any of the original three with nor and NAND? Yes, that is exactly the hint that I gave you. Okay, so you can. All right, and the key to that is De Morgan's theorem. All right, so again, we're not going to be asking you for to prove that, but think about it, because it would probably help you understand Boolean algebra better. All right, so far we had Boolean algebra, which was pretty straightforward, but now we of course make things more complicated. Now we say we can have functions, and it's like your life in middle school all over again. All right, first they tell you, oh, things are so simple, you just have those letters that stand for numbers, and that's it, and they throw in a few rules at you that you can apply when you're simplifying expressions, and then they say, oh, but now we have functions, those mappings between two sets of variables, and that's where things get a lot more complicated, because now you can have plots and graphs and all that business. All right, so the same kind of stuff exists in Boolean in Boolean algebra, and we have functions that operate on Boolean variables, and of course the result of their function is a Boolean value itself. So we already discussed it when I was showing this domain and range, and the notation we use the same as in our traditional middle school algebra. So we have f to denote some function, and in parentheses we write arguments. So this is a function of two arguments, a and b, and this is how the function is defined. So this is the rule for computing this function. Okay. All right. So we also can define a Boolean function using just their value of the function for each of their combinations of inputs. Okay. So there are different ways to represent a function. One is use their formula, algebraic operations. So like here we say it's a or b, and the other one is just to list all values. So here's a and b and f, and we have to list all their combinations, and then we have to define our function by just putting the correct value, right? So, and the function I defined here, you can see that it is actually a plus b. Okay, but we can define other functions, right? So as we already discussed, how many different functions we could actually build for two Boolean operands, right? It would be 16. All right, so this is something that I've just done, and this is what we call a truth table, right? A very easy way of defining function. If you have a relatively small number of arguments, right? If you have, two arguments, then you're only going to have 4 rows in this table. If you're going to have 5 arguments, then things get a lot more complicated, just because you're going to have 32 rows. Okay, so, and of course, the number of different functions that you can construct with 5 arguments is going to be 2 to the 2 to the 5th, right? So it's going to be a lot more different functions. All right, so here are truth tables for all our operations that we discussed so far, and so yeah, we already discussed all that. Pretty straightforward. Yeah, XOR, it's exclusive OR. It means that you can get only one thing but not two at the same time. So XOR is actually close to the OR in our common sense. Like, the example I think I mentioned before, like if I ask you, you want a candy or an apple, this OR in a natural language means exclusive. You cannot have both. You can only have either a candy or an apple. You cannot get both from me. Okay, so, and that's the kind of OR that in Boolean algebra we call XOR, exclusive OR, because with a regular inclusive OR, it allows you to get both a candy and an apple right here. And XOR exclusive, it says no, you cannot have both. You have to choose one or the other, only one. Yeah, or in English equals XOR in computer. Exactly, I like that. Very succinct and to the point. All right, so of course we can build truth tables for all different functions that here you see for 3 variables. Of course, our truth table has twice as many rows, so we have 8 rows, and we can just define the values for the function. So on the left, we have arguments x, y, and z, all possible combination of them, and on the right, we have the value of the function. Sometimes you will be told what the function is, like here, they actually tell you how to compute it. There might be other times when they only give you, f, so it's some function, and you might have to look at the truth table and guess or find out how to convert this truth table to a formula, right? So you might be asked, here's the truth table, please give me the formula. So like this part, which will not be given to you, right? You will have to find it out. All right, and so now the most fun we are going to have by delving a little bit deeper into, under the hood of a computer, into the electrical engineering side of things. Okay, so we're gonna be talking about, well, how those Boolean functions are actually implemented in hardware. And we start with gates. Yeah, you love gates. Yeah. Bill Gates or some other gates or just digital gates. All right. Gate is a digital logic circuit. So it's an electronic circuit, all right? We are not, things might be very different with quantum computing, but for now, all the hardware we have is based on electrons, so we call them electronic circuits, and so we call logical circuit a graphical representation of some electric circuit that performs certain function. So initially, we'll be mostly dealing with Boolean functions. So we have to look at how those operations that we discussed and or not are represented and how we can combine them as electronic hardware devices. Okay, so a circuit is built up of gates and other components, other electronic components. We just start with gates, and then things will get more interesting because we can have, we can combine those gates into combinational circuits and build a lot more complicated stuff. So each gate implements some simple logic function. All right, and here it is important to kind of abstract from the real implementation in hardware, right? So we not going to be going down to the level of transistors and actually discussing how, from the electrical engineering perspective, those functions are implemented. Okay, that would be the next level, but that clearly would be out of the scope of this class, right? It would really be an ECSE topic more than it would be a computer science topic. So, the level of exposure we get is those graphical representations of gates. Okay, they still correspond to, like, if you want to implement then this circuit in hardware, you would first have to draw this circuit diagram or schematic diagram using those, you know, boxes, so to speak, to represent certain functions. And then you would, probably select chips, or most likely it will be some programmable device these days that would implement this function using their actual transistors and gates and all that stuff. Okay, so we're not gonna go that deep. We only gonna go up to building, drawing circuit diagrams. All right, and there's a question: can we draw on paper and scan into our typed work for homework 4? The answer is no, and it will be described in the rules of homework 4. We will ask you to do everything in open circuits. Okay, and you will actually need to take a picture to include in your PDF file, and that is easily done in open circuits, but you will also need to give us the open circuits file so that we could actually run your circuit. Okay? Yeah, so you will be submitting circuit files. Not on the exam, of course. On the exam, because the exam is pen and paper, you just draw and that's it. But on the homework assignment, you will need to submit the actual files, and we will describe how this is done. Yes, you will do a lot of hands-on stuff with gates, right? Okay, so for us, because we agree that we're not going to discuss how this gate is implemented using the transistors. So we will just draw it as a box of a type, and then assume that this box implements the function that we need. So in the most general way, a gate, right, where we say a gate implements some Boolean function if it's a function of two variables. So the inputs are the variables, the arguments. Okay, so their inputs are traditionally shown on the left of the box, and then this box corresponds for the hardware that performs a certain function. So if a function is AND, it will perform this AND function and Boolean function on two Boolean arguments, and then the output is shown on the right and that's the output. That's the function that is being computed. So it's important to see that, whatever is inside doesn't really matter, but we assume that their output is tracking the inputs, and the output always reflects the state the state the states of the state of the inputs. Okay, so you don't have to kind of recompute or refresh. The output reflects the state of their inputs. So, and it's the easiest form of circuit, and it's called a combinational circuits because it has no memory, right? It just the output is directly straightforward in a straightforward manner the function of the inputs. All right, so gates compute something, right? That's important. That's why we're talking about gates, because we want to learn how computers actually compute, right? So how is computer able to do a plus b, 5 plus 7? How that actually is done, right? So, and the first thing that we mentioned is the output depends on the inputs. The output is a function of the inputs. The output tracks the inputs. If any of the inputs changes, the output might change to reflect the change of the inputs. Okay, and if the inputs do not change, it is guaranteed that the output does not change. Again, this is for this simplest form of circuits that we call combinational circuits. All right. So, and now the important thing is their notation. So the to distinguish between those boxes, we use slightly different shapes for them. So this is the shape for an OR gate, right? And so the inputs are on the left, their output is on the right. So this is the OR gate, and this is an AND gate, so that we can visually easily distinguish between the different types of gates. And this is a NOT gate, or negation or inversion. Okay, so those are three gates that we have, and here is their notation, the graphical representation for NAND and NOR gates. So you see, it's actually kind of we can just superimpose and not, or and not, right? So what we and you can read this very easily because the basic shape is gate, but then we have this circle here that stands for negation. Note how this is the same circuit here, the same circle here. Okay, so that basically says, well, do A and B first, and then negate the result. And that is exactly what NAND gate does, and the same for NOR. Okay, so you can you really need to remember there are two basic shapes. The AND has this straight side here, and the OR has this curvy side here. Okay, and then you can combine it with this circle here, which would just mean we want to negate the result. All right, so combinational circuits, we can put gates together into circuits. So we can combine, now that we have those basic gates, we can start using them as as bricks to build larger circuits. And our circuits, if we use those basic gates, no memory, then they would be just combinational circuits, which means that the output is a function of the inputs. Okay, so if the input changes, the output changes. And we can design circuits that represent any Boolean function. So let's actually do something. And let me discard all changes. And yeah, so please feel free to follow along with me to the open circuits. So here is the URL. And yeah, open circuits is actually an RPI Argus project. So this is their GitHub. So it was this project started at RPI. Yeah, thank you for someone putting the link in the chat. Good job. All right. So it's an Argus project, so it means it's just a bunch of students taking Argus class at RPI, decided to do this cool, cool system that they called Open Circuits to, to allow people to draw simple digital circuits and then kind of simulate their behavior. All right, so it's a great learning tool. It's not the only tool, and actually previously in this class we used another system that I will mention because maybe for some of the more advanced stuff we would have to use it. So this other system is called Logically. Okay, that's what we used before, and they have a free trial, which I was just using in the browser, so like that. Okay, so it's a little bit more advanced, but for at least for all the basic stuff, we're gonna be using open circuits. All right, so I want to pay my dues to their people, and they have a big team. It's like over 20 people actively working on open circuits now this semester too in Arcus class, so they are making improvements daily. Okay, and they're actively developing their system, and they're doing a great job. So I want to pay my dues to the team of Open Circuits and use Open Circuits for anywhere I can. And if I come across something that Open Circuits cannot yet do, I might have to resort to Logically. Okay, but I will try to stay with Open Circuits. Yeah, and of course, and when I asked Leon, who is the project lead of Open Circuits, like what was their largest number of users they had at the same time using Open Circuits, they actually didn't. They actually did not know. So if we see that there are any problems with 200 people accessing Open Circuits at the same time, if we if we see any other bugs, of course their requirement to submit circuits made with open circuits will be lifted. Okay, of course, we know, we are trying to stay aware of any problems, and of course, we don't want you to be responsible for something that is beyond your control. Okay, so I'm keeping my fingers crossed. Open circuits behaves well, and we all use it and enjoy it. But if something goes wrong, of course, we will adjust the requirements. And they recommend that we use nightly version because it has more features. I don't think there's stuff that we, at least initially for the first, few lectures, I don't think we're going to use anything advanced, but, so you may try using, the stable build open circuits IO, not nightly open circuits. All right. So let's actually try drawing something. All right, so here, and you can see my open circuits window, right? Okay, cool. All right, so we want, let's say, to have an AND and a NOT, and combine them, and I want to have an AND and two NOTs wired like that, and I want to have an OR wired like that. Okay, yeah, I need an input. So for the inputs, we can use either constants, 0 or 1, or we can use those switches or buttons. So let me use the switches, and I will wire my switch to all the inputs that I have. Okay. And we want to observe the output, which is I like this LED thing. For something more advanced, we might use those displays, but for just Boolean stuff, this is fine. All right. So I just built a very simple combinational circuit. Why is it called combinational? Because its output depends purely on their inputs and nothing else. Okay, so if I don't change anything, my LEDs do not change, right? These two are lit, their bottom one is not lit, and it's gonna stay like that unless I start changing the switch. Unless I start toggling the switch. So if I toggle the switch, you see how the color of the wires actually indicates their high or low level, true or false. It makes it easier to debug. So you see that now these two LEDs are lit and this middle one is not lit. Okay. All right. And clearly it is a combinational circuit. Okay. Note that the middle LED does not change as I flip the switch. So an output does not have to change when I change the inputs, but it may change. Okay, that's the important thing to remember about combinational circuits. All right, so and what do you do with, imagine this is the circuit that you need for your homework. So how do you download it? So you first and you can download it. So this is the most important thing. You can download it as a file. So, and it's going to be a circuit file, a circuit, so in folder, and you can see it just, this dot circuit. Okay, so when we ask you to submit your circuit as a file for the homework, you just submit the circuit file, and you would have to rename it because we tell you how to name the file. So it would be something like homework 4 circuit. Maybe there will be more than one circuit, so we will tell you how to name the files. Okay. So yes, homework 4 will contain circuits for sure. Okay. All right, and then if you need to do a screenshot for your PDF, all right, so we ask you not just to submit the circuit file, but also to take a screenshot and include it in your PDF. So this feature, I was told, does not currently work. Yes, and it still doesn't work, so maybe they will implement it shortly, but it's not a problem because you can always take just a screenshot and, something like that. And so as you can see, it's if you save it here, okay, it's just a screenshot, okay, and you just include it in your PDF. All right, so that's it, and let's look at now the actual circuit that I tried to do here. So this upper one is AND with a NOT, okay, so it's an NAND, and I can verify that it is an AND. All right, if I use this, why are the same inputs? And look at their output. And as you can see, I'm learning this along with you. I don't remember how to pan. Okay, I got it. It's a middle mouse button. All right. So, and if I, flip my switches, I see that, well, no matter what I do, my two upper LEDs are exactly the same. Okay. But to verify that they actually perform the same function, you have to check all combinations of inputs, all 4 of them. So if I start with everything turned off, 0 and 0, okay, and so you can have a label here, right? So you can say, if I don't like this, you can say label A. So input A, input B, okay, so something like that. So please, in the homework, you will need to label everything, okay, but this requirement will be spelled out. And so, we start with both A and B at 0, then B goes 1. We see that these two LEDs are still showing the same value. It doesn't matter which value, right? If we are just trying to establish that, these two circuits implement the same Boolean function, we just care that they are the same for all combinations of inputs. So, and then we try this, they're the same, and then the fourth combination, 1 and 1, we see that they are off. Okay, so that's how we can see that this single NAND gate performs the same function as AND followed by a NOT, quite predictably. Okay, and now let's look at this part here. Okay, so we first invert A and B, and then we route it to their AND gate. All right, so if I want to put a label here, what is the function that this part of the circuit implements? All right, so, and I can write it A and I don't know if there's a dot here, but let me use asterisks for now. Okay, so this is not A and not B. Okay, all right, so what about this? This is simply A or B. Okay, all right, so now I want to implement come on. This. Okay. So, and to do that, I need an OR and a NOT. And I use the same inputs. Of course, you don't have to. You can, use different inputs. I just want to make sure that all my, sub-circuits use the same inputs for now. And then I need the LED. And actually, let's use something else. Let's use the BCD display just for fun. All right. No, I don't think I wired it properly, so let me rewire it. Yeah. All right. So, and you can see that it, with this BCD display, you can actually show 0 or 1, in this form. Okay. Yeah, you can also color them. Yeah. Here's the color. All right. So now my question to you, please help me implement the same function, but using the AND gate. So I want the same function as this one, but using an AND gate. So as I'm wiring the inputs, please let me know what I need to do. De Morgan, exactly. So which additional components do I need? Let's say I cannot use OR gates. All right, I need 2 NOTs. Where do I put 2 NOTs? Exactly, so I need to I need to negate my inputs, and actually I'm going to reuse the NOTs that I already have, okay? So this is another thing. If you already have some output that performs the function that you need, you don't have to repeat it. You can just reuse the same output again. In the logical circuit, it is perfectly allowed. In a real electrical engineering design, you would have to be concerned about the load, because every integrated circuit, every actual electronic device has a loading capacity, so you cannot connect infinitely many loads into any output. So there is a drawing current max capacity, but for logical design we just ignore it, so you can connect as many you know use a particular output as many times as you want. Okay, all right, so that's that. And let me do the BCD again. All right, and now let's verify that these two actually perform the same function. All right, and so I can leave it like that, because the formula would be different, but if it's the same function, it doesn't matter which formula I use to express this function, right? So, but let me type it like that. Not A times not B. Okay. All right, so they are both at, and let's start with both zeros. So their output is for both of them is at 1. I flip both zeros. I flip both zeros and both zeros. Okay, so I clearly see that for all combinations of inputs, the output of these two circuits, they match, which means they implement the same function. Okay, yeah, and yeah, you don't have to the logic gates that are available to you, you can just use them. You don't really have to build them from multiple gates, but you can. So it's important to see that this NAND is nothing more than AND followed by a NOT. Okay, and you can actually, one other thing that you can change is the number of inputs. So you can have gates that have more than 2 inputs, because you can have functions that take more than 2 arguments. Okay, so that is totally possible. So will next week's exam be like half MIPS, half Boolean algebra? Yes. There will definitely be MIPS with procedures and array and saving stack and saving S's and T's. So everything that we discussed last lecture, and there will be definitely this material on Boolean algebra and circuits and that kind of stuff. All right, so yeah, we'll see how far we go today. All right, so and we just built similar circuits, right? So this is another example, right? And here is their question. That's our next pop quiz. What is the output? Which formula expresses their function computed by this logic circuit? And let me open. So I believe this is our poll number 3. Okay, so hopefully it's the right one. And we are moving on. All right, so we now have the third. We just discussed the third way to define a Boolean function. Okay, so it's a circuit. So we can give you a circuit, and that circuit would define some Boolean function. We can give you the equation like a plus b, a or b, or we can give you the truth table. They are all different ways to define a Boolean function. All right, and implementation would be exactly the logic diagram that we have seen. So you just grab the gates and connect them, wire them up, and yeah, that's it. So in a real electronic circuit, electronic device, you would also need to take care about the power supply and a bunch of other stuff that electrical engineering is concerned about to actually make this circuit work, right? But for the logic design, don't worry about the power source. We assume that power is given to us by some magic being, and we don't have to worry about it. Yeah, infinite power, exactly. All right, so integrated circuits are actually, the simplistic view is just it's a bunch of gates packaged together. And a long, long time ago, in a galaxy far away, you could actually buy their ICs, the integrated circuits or chips that would contain things like that. Like, this picture here is a real chip that is probably 40 years old now, and it's no longer used because it's just too low, low level of integration. It's you know that there are a lot more powerful chips now that contain probably millions of those gates. Okay, and so it's no longer used, but it's a convenient model to look at, and it's a real thing, right? So like 40 years ago you would actually buy those chips, and they would contain like those four AND gates, and then you would just build your entire circuit from that. And of course you would have to for any realistic, any more or less complicated device, you would have to use hundreds, thousands of those chips, and you would have multiple PCBs, multiple boards, and stuff like that. So these days, of course, the integration level is much higher. So you can basically buy one chip with multiple many pins. In many cases, several hundred of pins, and then actually program that chip to implement the function that you want. So we are in the era of programmable chips, right? So you have to write software to actually program a chip. So there's more languages for that. And if you read your textbook, then this language, one of those languages, one of the most popular languages for doing that, for programming, for writing programs for chips, is actually described in our textbook. It's called Verilog, and we're not going to cover it in this course. It's very exciting. It's thrilling, but that would be too much for this course. But if you're interested, please please read it. And since I mentioned that, let me point you to something else. All right. So here in our course materials, I posted under reference materials. So I posted a bunch of PDFs that are additional additional material for our textbook. So our textbook only the print version only contains some core material, and the authors made additional material available to anyone for free. So even if you didn't buy the textbook, well, I know all of you did buy the textbook because it's required for this class, but if you didn't buy the textbook, you could go to what is called a companion site for the textbook and download those PDFs. So those PDFs are not copyright protected because they are not in the print textbook. They are just additional material that authors didn't want to include in the printed textbook, but wanted to make available to everyone. All right, so those please read through those, and one of them is this Verilog tutorial. So if you read one of their in one of the appendices, I think it's appendix A, either A or B, probably A. Right, there's a chapter on there's material on Verilog, and then there is this tutorial on Verilog. So if you feel interested in that topic, please take a look. It's exciting. All right, and we are back to here. All right. And we just talked about implementing Boolean functions. So Boolean function can be expressed as a formula, as a circuit, as a truth table, and we can actually come up with different implementations of the same function. And we just saw that in open circuits in the examples that we've done. So, and we've seen that it is actually possible to implement the same function using different number of gates, depending on, it's kind of equivalent to, if you start with a formula, you can, let's say you have a formula, you have a Boolean expression that uses 5 pluses and 10 dots, and that would correspond to the number of gates that you need to use to implement this formula in a straightforward manner. Just one to one from their Boolean formula, from their expression. But then it turns out that maybe by applying some Boolean algebra laws, you can simplify this expression so that it uses fewer operations, fewer pluses, fewer dots. And then, of course, if you transform this expression into a simpler form with fewer operations, and then you implement this formula instead of the original formula, you're gonna need fewer gates. And of course, this is desirable, right? This is good. We want to spend as little money on our gates. Imagine you have to byte each of those gates. Imagine that you have to pay for each of those gates. So of course, we want to minimize the number of gates. All right. So here is an example, and we have this this formula here, okay, which is a times not b, a and not b, or not a and b. Okay, and then we compute this f, this function given by this formula. So it would use 3 gates, right? We're going to need 1 OR and 2 AND gates, and yeah, if we build the truth table, we realize, oh, this is really an XOR function. So we have a gate, just one single gate that can get us this same function. So instead of using 3 gates, we can use just 1 gate. Okay, of course it's easier. It's less hardware. Okay, so this is one implementation, just straightforward implementation of our formula, right? We have to have negated A and B, so hence our 2 inverters here. So the not gate is also known as an inverter because it inverts the value, and then 2 ANDs and then an OR here. Just straightforward from the formula, right? And here is another implementation of that. Okay, so how many gates do we have here? So we have 2 AND, 1 OR, and 2 NOTs. So we have 2 NOTs, 2 ORs, and 1 AND. So it's slightly different, but in terms of the number of gates, it's the same. So you see that we just applied one of their laws, one of the transformations to switch it from this form where our function is the sum of products, right? Because we can treat this as a sum, as a Boolean sum, and dot as a product, from the sum of products into the product of sums. And we didn't gain anything in terms of the number of gates, but it's a very interesting observation that will be important. All right. And to prove that it's actually the same function, right, we have to do some work. Here's how you do it. So please review that. For every step, we specify which law or which postulate we use. So each step, and when we ask you in the homework to prove something is the same function as something else, that's how you do it. So every step you have to explain what you do, right? You cannot just eliminate stuff or perform some combine 2 or 3 steps into one. You have to spell out, you have to justify each step by specifying which law you used. Okay. All right, and then logic design. So we just talked about simple components, but we can also come up with some hardware that is very useful in processor design. So you can build everything from those simple gates, but there are components that have more complicated functions, and we oftentimes want to just talk once about how this more complicated device is built, and then represent it with just a box. Okay, and that box inside will contain all those gates, maybe dozens of them, maybe hundreds of them. But we want to, once we discuss how this is done, we want to abstract from the implementation of that particular component and just use it as a black box, as a component that performs the function that we need. Okay, so we will use those components when we design control systems later. We will build our own processor. Okay, so just a heads up, it's coming up. All right, so let's look at their components, at some of their components that we need to build our processor. And this stuff is extremely important because later on our next topic in a couple of weeks, maybe less, is actually looking at the design of the processor. And you will have this big diagram, okay, that will be using the components that we are discussing now. So if you do not understand the material that we talk about now, you will be definitely unable to understand the data path diagrams, the diagrams that show the internals of the processor, because it will be using the components that we discuss now. Okay, so it's extremely important to understand this stuff now. Yeah, it's a little bit of computer engineering. I agree, but it's useful for all computer science. And I believe, of course, you're free to disagree, but I believe it is useful for all computer science people to at least know how this is done. Okay, we will not be asking you to build, a more or less complicated processor or a real world processor from scratch. Okay, that would be too much. But you need to understand how processors work and how, because that answers the question how computers compute, how this is actually done. All right, so first components that we talk about are decoders and multiplexers. So both are important, but multiplexers are especially important. They are you're gonna see a lot of multiplexers, okay, in the future lectures. All right, so let's start with decoders. A decoder has n inputs and two n outputs, and the function that the decoder implements is the inputs are used to select which one single output is turned on. So only one of the outputs will be activated, will be at true or 1, and exactly which one is determined by their inputs. So we have n inputs. Essentially, they encode their output that should be activated. So you can treat those n inputs as an n-bit number, and the output with that number will be activated, will be true, will be at 1. Okay, that's why it is called decoder, because it takes encoded number with n inputs and it decodes it so that it activates only one of the outputs. For multiplexers, and no, the multiplexer is not the opposite of a decoder. So, the opposite of a decoder would be an encoder that has two n inputs and n outputs. Okay, so it's also a component that is used, probably not as much, but it is a useful component. That would be the opposite of a decoder. Multiplexer is a component that basically allows you to route an input to the output. So multiplexers have two n inputs, 2 to the power of n inputs, and selection bits. So those selection bits are also inputs, and 1 output. So selection bits select which of the inputs is connected to the output, is routed to the output. Okay, and this is a very, very important component because if you think about it, it's like a programmable switch, right? So you change those selection bits and they rewire their input to the output, right? So they rewire which input gets connected to the output. All right, so this is a decoder, right? So two inputs, which means that there are 2 to the power of n outputs, so 4 outputs, and this is the truth table of a decoder. Okay, so as any combinational circuit, you can express it with a truth table, right? In this case, it's just 4 functions at once, O0, O1, O2, O3, and two inputs. Okay, so, and the way it works is if you look at the inputs as the number, so, and it's binary, so it's 1 and 1, which is 3. It means that O3 will be 1 and all other outputs would be 0. If my inputs change, and let's say my inputs are now 0 and 0, then 0 and 0 is 0, so it's number 0. So it means that 0 output, O0 or not, will be activated, will be 1, and all other outputs would be 0. Okay, so you see how decoder actually decodes their number from basically their binary form into one output wire, one output that will be activated that corresponds to that number. Okay. All right, and this is the truth table. So you see for when both inputs are zeros or not is 1, the rest are zeros. And note how if you look at any column, okay, only one input, only one output is activated. O1, O2, O3, only one. The rest are all the remaining 3 are all zeros. Okay, that's their rule. That's how the decoder works. Okay, and then from this truth table, we can build their formulas for each of the outputs. Okay, so remember their circuit, their truth table, and the formulas are 3 different ways to express a Boolean function. And you should be able to use any of them as the input and then produce the output. So if we gave you the truth table or the circuit, you should be able to come up with the formulas, because quite often with the formulas you can do your Boolean algebra laws and maybe simplify those formulas. We shall see how this is done. So, and here we had this decoder as a black box, but it can be implemented using gates, because once we've written our expressions, our formulas using and, or, and negation, we can actually build our decoder with our basic gates. And this is exactly the decoder. Okay, and now you can just look at any one of their outputs. Okay, so it would be not I0, not I1, ANDed together. And this is exactly what happens. We have an AND, which takes a negated I1, negated I0, and ANDs them. That's the definition of O0 or not. All right, and of course we can have decoders with more inputs. So with 3 inputs, the decoder would have 2 to the third 8 outputs. And that would be the truth table of that decoder. Again, the same principle applies. Only one output is activated at any moment of time. All other, we also say in electrical engineering, setting something to one set, we say assert, right? So O0 is asserted here, and all other outputs are deasserted, okay, or are not asserted. So it means they are at 0. All right, and here are the corresponding Boolean expressions. How do you get Boolean expression? Just from this truth table, okay? So this is the logical kind of progression, and then that's how you implement your 3 input decoder or 3 decoder. And it's only partial implementation for only 2 outputs, but you should be able to implement the rest of them, O2 through O7, by just looking at those formulas and selecting the proper gates. I highly encourage you to actually do this in open circuits, just to get the practice, and then make this circuit, make this 3 decoder from basic gates and, or, and not, and then connect switches to I0, I1, I2, connect your LEDs or the BCD display to the outputs, and flip the switches and see how outputs change, how outputs behave. Right, so we can also perform a useful simplification that I mentioned. If you have this, all right, you don't have to use 2 AND gates. You can use one single gate with more than 2 inputs. Right, so you can use 3 inputs, a 3 input AND gate as in this example, and I showed you before how to do this in open circuits. You just put 2 instead of, you put 3 instead of 2, or whatever the number of inputs you need. All right, and with that simplification, if you have access to 3 input gates, you can build your 3 decoder in fewer gates. Okay, so let's stop here at slide 60, and then we will pick up from here on Tuesday. So thank you, everyone. And yeah, we had very few questions in the Q&A this time. So maybe we need to reduce the number of panelists because otherwise they're bored and they're not, 5 people for 8 questions seems a little bit excessive. Well, anyway, thank you so much, folks. Enjoy your weekend. And yeah, vote for our polls from today. And I will see you on Tuesday. Thank you.